All right, so it is top of the hour here. Maybe we can actually formally get started. And maybe a few more people will trickle in. It's my great pleasure today to introduce Joseph Thywissen for today's VAMOS seminar. Joseph's a professor of physics at the University of Toronto, where he's been since 2003. Prior to that, he got his PhD at Harvard University and spent some time in France in Alain Aspec's group as a postdoctoral fellow. Especially an honor for me to introduce Joseph, who is my PhD advisor. So I got to be one of his first students and know his lab very well. So it'll be exciting to see the work that they've been doing in the last few years. With that, I guess I'll just mention one more time, if you are in the audience and have any questions, please use the Q&A feature. Joseph will stop a couple of times through the talk, so please add your questions as they come up to you, and we can address them as we go, as well as sometime at the end. And if you're watching on YouTube, likewise, you can use the chat feature there to ask any questions. Yeah, with that, Joseph, please take it away.
All right, great. Thanks, Lindsay. It's an honor to give the virtual AMO seminar, which must be, after you count all the watches on YouTube, one of the largest seminars in our field. And so today I'm going to tell you about some recent work in our lab on orbital interactions between fermions in confined geometries. So the main theme of everything I'm going to tell you today is that the many-body wave function of fermions must always be odd under the exchange of any two particles. So if you're describing a many-body wave function for n particles, and I exchange the location of just two of those particles, the wave function must be the same except for an overall minus sign. And so this is true for fermions, whether they're hot or whether they're cold. And what I'm going to tell you about today will often reduce the problem down to just two particles, and that two-body wave function of particle 1 and 2 can sometimes be written in a product of two different parts, one which is just the relative wave function, and the other which is the center of mass wave function. And so now if I do this operation where I exchange the locations of particles 1 and 2, the center of mass wave function is unaffected, but the relative wave function acquires a minus sign in its coordinate. So if I show you a relative wave function that is then odd in that coordinate, in that relative coordinate, then it already satisfies exchange symmetry. And so this is the kind of relative wave function that all fermions must have. So this story should be familiar to people who know about partial wave expansions of scattering. And there, that relative wave function is always written as a sum of spherical harmonics times a radial part. And so one can write Schrodinger equations for these radial wave functions once you've separated them out into spherical harmonics. And the symmetry property of these angular wave functions are that if I do that particle exchange, where I again go from r to minus r, then I get a -1 to the L, where L is the angular momentum of that partial wave. So for even L, such as L equals 0, which are S waves, the exchange parity for the two-body wave function is even. And for odd L, such as P waves, the exchange parity is odd. So fermions, which are spin polarized, must have L equals 1 or L equals 3 or odd orbital partial waves in order to have this essential exchange process. So today's talk is a story about this kind of p-wave scattering. I'm going to write sometimes these kind of symbolic wave functions. One of them is the m equals 0 projection of the L equals 1 orbital wave function. It looks like this kind of dumbbell. And the other is, I'll often write as the superposition of the m equals ±1 states. And so these look, familiar to you from the hydrogen orbitals of a central force problem. And there too, of course, the orbitals are breaking down into spherical harmonics. So the outline of what I'm going to talk about today is I'm going to tell you a little more about p-wave interactions and some background. And then I'm going to tell you about how we isolated triplet pairs, identical pairs of fermions, and studied just two-body interactions. Oops. And then I'm going to tell you about what happens when you confine these particles in a quasi-one-dimensional subspace. And the most interesting thing that happens is that we find, surprisingly, an emergent S-wave scattering in that one dimension. So another important piece of this puzzle that might be familiar to many people watching this talk is that we can control the scattering between ultra-cold collisions in certain conditions where we're close to what's called a Feshbach resonance. And the physics of that is that the particles colliding already have an interatomic potential, but there might be another pair of quantum numbers that pair of atoms could have, a molecule which is weakly coupled to that open channel, often through a hyperfine interaction where an electronic and a nuclear spin flip, conserving the total projection of angular momentum. In that case, when the scattering is close to the energy of this closed channel, the phase can be sensitively dependent on the relative energy of the closed channel and the open channel, the energy of the initial collision. We can tune, if the closed channel has a different magnetic moment than the open channel, then we can tune that relative energy with an ambient magnetic field, and that's what a Feshbach resonance is. So Feshbach resonances are usually used to control S-wave scattering. And here's some data from the Rice group showing a cloud of bosonic lithium-7 in otherwise similar conditions, but at different magnetic fields. So these dipole-trapped atoms are sitting in a tweezer you can't see that's horizontal in these images. And the differences between images A, B, C, and D are that the scattering length is, and the interaction between atoms is strong here and weak here. And they're choosing that scattering length by choosing the ambient magnetic field, which you also can't see in the images. In this last image here, the scattering length has crossed through zero and is negative, and the Bose condensate breaks up into solitons. So you can take an image like this and analyze it and extract what the scattering length must have been at each magnetic field. An analysis like that gives a scattering length versus field, which varies from 10 to the -2 to nearly 10 to the 6 Bohr. So that's something like picometers up to microns. And all of that is just with a tuning of magnetic field. It's really an extraordinary tunability. And when this scattering length gets large, then the scattering cross-section passes what the maximum scattering cross-section could be for S-wave scattering. And in that regime, scattering saturates to something called the unitary limit, where the cross-section for two atoms to collide is controlled by the de Broglie wavelength, or equivalently, the relative wave number between the two atoms. So this happens when the scattering length is comparable to either that de Broglie wavelength or 1 over the Fermi momentum, which gives a typical interparticle spacing. Now, all of this happens for S waves, and this interesting unitary limit is interestingly scale invariant as well, because once the scattering length drops out of the problem, the only scale left over is the interparticle spacing. And so therein lies a regime of physics where you can look at things like equations of state or dynamics, which should be true for any unitary interacting fermions. One can also describe S waves in terms of a pseudopotential, where the interaction between atoms can be written in a very simple way as a delta function between the interacting pairs, where r is the relative coordinate. Now, the actual interaction isn't a delta function, but if I tune the amplitude of the delta function to give the right scattering phase, and the scattering phase is what you get from the real potential, which can be expanded in momentum like this. So long as I choose the right prefactor of this delta function, I get all the right physics for the low energy degrees of freedom. And so this is one way of talking about the scattering length as an energy dependent prefactor on this pseudopotential. And once you write out the pseudopotential, you can write out a many-body Hamiltonian and explore theoretically and experimentally interesting many-body physics with S waves. So the cotangent of the phase for S waves looks like this, and I'll come back to talking about what this expansion means. But let me just say that at unitarity, the scattering phase goes to pi over 2, so that this cotangent times pi over 2 goes to 0. And that's also where the scattering length diverges, as I showed you in the previous plot. And that means the prefactor of the pseudopotential diverges, and yet the whole thing works out because the pseudopotential just enforces a boundary condition. P waves work in much the same way as everything I've just said. So if I tune the magnetic field in the right conditions, there is a Feshbach resonance, and the scattering volume near that Feshbach resonance diverges. Here, this inset shows the inverse scattering volume for the particular resonance we use. And right at resonance, the scattering volume should be infinity, and that matches coupled channels calculations, which also match the observed binding energies of P wave dimers quite well. However, there's a big difference between P waves and S waves in that the subleading term is always important. And so the cotangent of the phase now goes like 1 over a thing that looks like the scattering length, but now has units of volume. And then there's a second term, which has a correction to that, an energy-dependent correction. But notice that this second term here goes like 1 over momentum. And so that in the cold limit, it becomes more and more significant. Whereas if I go back for a moment and I look at that S wave expansion, this also had a subleading term, but here as K got smaller, so as the energy of collisions gets lower, it becomes less and less important what that subleading term is. So for that reason, P waves are often described with 2 parameters instead of 1 parameter. And this other parameter, the effective range parameter, doesn't change very much around the Feshbach resonance. You can write down several models, but it kind of just changes linearly in the couple Gauss around resonance, and it can't go to infinity. It would be nice if it could go infinity, then you can get rid of this term entirely, but it can't. It's always of the order of the van der Waals length. So with that in mind, let's think about now what happens in the unitary limit. I want to say one more thing, which is that you can also write out a pseudopotential, and the pseudopotential does have a delta function, just like for S waves, but it's a little more complicated. You have to do a kind of derivative that acts as an operator both on a wave function to the left and the right of this pseudopotential operator. It also has a prefactor which scales like the scattering volume, and I can do all the same things for P waves as S waves. I can write out the scattering volume as a function of energy, and that can be then written out in terms of these energy independent scattering volume and effective range that I showed you in the previous slide. So at unitarity, what happens to the pseudopotential? Well, the scattering phase goes to pi/2, and then the scattering volume at that place is going to plus or minus infinity, which again seems a little odd that I have a potential which is diverging, but in fact the expectation value doesn't diverge because it enforces a boundary condition on the wave function that this whole operator goes to 0. Otherwise the problem energy diverges. Even though this pseudopotential has been written down as long ago as in the 70s, it's never really been tested to predict an energy of a system because P-wave systems have had some problems, and I'll come to those in a moment. So now let's talk about unitarity and scale invariance. So I mentioned that for the S-wave case, when we go to unitarity, then we can have this term which is divergent, so we get rid of it, and now we just have the subleading term, but if we're really cold, that goes to 0. And now the cotangent of delta must equal pi/2. Here, for your reference, this is what cotangent does as a function of phase, and pi/2 it goes to 0. So in this regime, the scattering phase stays pi/2 for a whole range of k, so long as these conditions are both met, which get easier and easier as energy gets lower. And as a consequence, you get to a beautiful regime of scale invariance. The articles in this book by William Zerger give you some flavor for what is possible there. So let's do the same thing now, except for P waves. And okay, we can again make the scattering volume diverge at a Feshbach resonance, and then we have this subleading term left over, but that subleading term diverges if I go to a very cold collision. And when this goes to infinity, it means the scattering phase goes to 0. So for low energy, even at the Feshbach resonance, you get no interactions for P waves. And for that reason, there's no corresponding universality that appears right at the Feshbach resonance. So this is kind of disappointing. But still, you can tune the interaction strength. I mean, you don't necessarily have to have a scale invariant regime in order to have an interesting physical scenario. So P waves have remained interesting to people. And let's see. I guess let me just emphasize one more thing about this, that the energy scale, the energy width of scattering right around resonance, if I tune this resonance to the Fermi energy, and I think, okay, now I can make a strongly interacting Fermi gas. Well, if this is EF, then the width here in energy is only a fraction of the Fermi energy. So this Lorentzian fit to scattering cross-section versus energy has a width which is characterized by this dimensionless parameter, again, this effective range, which we can't get rid of, times the typical Fermi momentum. And it turns out that this parameter is always small. Okay, so despite the lack of a universal regime, there's really sustained and broad interest in P-wave interactions. And the reason is that you get exotic quantum phases when superfluids can P-wave interact. The crossover physics that exists in S-waves becomes a phase transition, and it's known that there are topological edge states for those kind of superfluids, and those are much discussed, in part because this is one route to making topologically protected qubits. Another interesting thing is that in transport, you get viscosities that now depend on momenta in different ways. You break the symmetries that existed in the S-wave scenario, and things become kind of interesting. And people have worked on that in a number of different papers. And finally, there are a lot of predicted few body physics states, for instance, trimers that have been as yet unseen, and an interesting role of dimensionality. For instance, there are no Efimov states in 3 dimensions, but in 2 dimensions, there's something called a super Efimov state, which is yet to be seen. However, in all of cold atoms and condensed matter physics, only helium-3 remains the P-wave superfluid that everyone agrees upon. There was a strontium ruthenate candidate for a long time, but it's now thought that that's actually an S plus ID kind of order parameter. And so there are new hopes out there for materials, but so far as we know, the only P-wave superfluid we've been able to play with is good old helium-3. So in cold atoms, P waves have been understood to be relevant and controllable for over 20 years now. In Debbie Jen's lab, they observed that even though for spin mixtures, you can see S waves, for spin polarized gases, you must have P wave scattering. And far from a Feshbach resonance, that means the scattering is suppressed by the centrifugal barrier as you get colder and colder. Here you can see that if the typical temperature of the cloud they were looking at was below 100 microkelvin, then the cross-section just went down, essentially because atoms would be rolling off of the centrifugal barrier, which means they're non-interacting. However, around the Feshbach resonance, which I've already told you about, they found in 2003 that they could enhance quite a bit this cross-section by 3 orders of magnitude above its background level. And around the same time, several other groups were seeing P-wave interactions, and they were explored in theory and in experiment in a wide number of groups around the world. The issue is 3-body loss, that along with this enhanced scattering cross-section, one finds enhanced 3-body loss coefficients. Here's a study of 3-body loss in potassium-40, but similar stuff has been seen in lithium-6. There's a state where you can suppress all 2-body loss, but not 3-body loss. So in particular, in the Mukayama group, this has been explored, and some beautiful physics has been seen in this 3-body loss parameter. So what we've done recently is turned off 3-body loss by isolating fermionic pairs in a very deep optical lattice. And so I'm not going to tell you too much about how we set this up, but just what we observed. With pairs in the lattice, we could see interactions between one atom and another atom in the same state But if the lattice is deep enough, then tunneling is shut down between these sites. So the way you can think of each of these sites in a deep lattice is as if it's just a harmonic oscillator. And in this harmonic oscillator, the frequency gives you the band gap between the lowest and the first excited state for a single particle, and the confinement is much less than 1 interlattice spacing. In our case, the harmonic oscillator length was about 50 nanometers. And at first you might think this is exactly what you don't want to do to avoid a density-dependent loss process, because if I just calculate the density of atoms on a single site, it's huge compared to what you have in a free gas. So if I blindly plugged in a 3-body loss parameter, then you would think that the gas lives for something like 30 nanoseconds. In fact, it lives for milliseconds, tens of milliseconds, because there is no third particle to induce this 3-body loss. So this allowed us to study the interaction between pairs of atoms as a function of lattice depth and magnetic field. The kind of measurement we would do is we would start with atoms in the correct motional states to p-wave interact, but in a background state that has no Feshbach channel. Then with a 2 RF photon flip, we would flip both of these atoms into an interacting state. But in the interacting state, because of the interaction energy, we would need to provide with the RF either more or less energy in order to have a repulsive or attractive final state. And so the kind of spectra we observe is something like this. Right at the single spin flip resonance, some of the singly occupied sites in the lattice have their spin state changed from this blue to this orange state. At slightly detuned below, this is in kilohertz, sorry, at 20 kilohertz below, however, we saw another peak, which was responsible for flipping these weakly interacting atoms into attractive interacting states. But also, for the same initial conditions, we could, at a higher frequency, flip into a repulsive state. So at first it seems strange, but let me show you what theory predicts this should look like. At any one magnetic field, this is a multi-branched energy spectrum with an attractive state and a repulsive state accessible to you at a given magnetic field. And so what we're doing basically is jumping into this diagram from a non-interacting diagram and landing somewhere in, actually around this n equals 1 state. And so what I mean by n equals 1 here is that the relative motion between the two atoms is has 1 quantum of vibrational energy, and that's the kind of state you would expect to have p-wave interactions in and have fermions in, because you have this exchange anti-symmetry for odd harmonic oscillator states. Okay, so now we repeat that kind of measurement for various magnetic fields and various confinements. And what we observe is a complex structure at first, that at various magnetic fields, we would see multiple branches. It's complicated by the fact that there's not just one projection of p waves, but there's this other projection I told you about. And so we could be flipping either into pairs that are have L equals 1, ML equals plus or minus 1, or into pairs with ML equals 0. And so that explains, this kind of dark and light structure here when we calculate. And then there's the attractive branch, which I mentioned. And so here's a Feshbach resonance where the energy is shifting up quite quickly as magnetic field is changed. But then if I repeat this whole experiment, instead of at 90 kilohertz confinement frequency, but more like 130, you see everything is shifted up. And so there's a confinement-induced shift of that Feshbach resonance. So this seems quite complicated, but once we rescale everything by harmonic oscillator degrees of freedom, there's a nice data collapse. So if I replot the vertical axis in terms of the harmonic oscillator frequency, h bar omega, and instead of magnetic field, I use the energy-dependent scattering volume at the magnetic field of measurement, then all of the data sets I've just shown you, as well as a few others, collapse onto these single sets of curves. And so these are the predictions, these various colors here for these confinements. And you see that as we tune the scattering volume, the energy-dependent scattering volume, we go from a non-interacting state all the way up to one full quantum of additional energy in interactions. And that is the unitary point. So at this point, the scattering volume has diverged, and the energy of the particles here doesn't depend on the scattering volume anymore. It's now just given to you by h bar omega. And because this is a multi-branch structure, this repeats at every branch, and the two we could access are the lowest attractive branch and this first excited branch. So another thing I want to point out about this plot is I'm showing you theoretical curves that were made with a pseudopotential theory. So let me remind you what that looks like. The pseudopotential theory is this crazy looking modification on the S-wave pseudopotential where we have these directional derivatives. But if I take this directional derivative form of the pseudopotential and I put it into the harmonic oscillator states, in this paper, Idziacek showed that you get the spectrum I'm showing you here. So now we can also calculate not just energies, but wave functions. And the pseudopotential gives the blue wave functions at locations A, B, and C I'm showing you here. And we can compare the predictions of the pseudopotential to a full coupled channels calculation of the wave function done by José Dencao. And you see that it matches extremely well up to an interatomic distance, which is less than 1/10 of the harmonic oscillator length. And so at that distance, there's a difference. The pseudopotential diverges. We need to cut that off to get reasonable energies. But once we choose that cutoff, then we can make all of these predictions, and it agrees with what we observe. Okay, so let me pause here for questions. That's kind of the first half of what I wanted to tell you, basically.
Okay, thank you. Yeah, people can add their questions to the Q&A here. I was going to ask about the, I guess I hadn't really appreciated before this idea that you have to be in certain vibrational levels of the pairs in order for them to P-wave interact, as you say. How do you prepare such a thing? I mean, I guess it was just my question.
Right. There's a background story to this, which is that if you have, let's see, if you have a harmonic oscillator of a single site, and I put a fermion in just the lowest vibrational state, then I can't put another, let's say,
Right.
spin down fermion there. I should either put a spin up there, in which case I get interaction energy. The next spin down I can create is this one. And so now what is the relative degree of freedom between this n equals 1 and n equals 0 fermion? Well, the relative degree of freedom is looks like an n equals 1 harmonic oscillator. And so yeah, I guess you can say it's something like the anti-symmetrized combination of the harmonic oscillator psi1 for particle A and psi0 for particle B, let's say. If I anti-symmetrize that, I get a relative degree of freedom, which is n equals 1 as a harmonic oscillator, and then a center of mass coordinate, which is psi0.
Okay.
Yeah.
All right, and I guess the other question, and I maybe I've asked this before, but is there a good physical interpretation for this effective range? Like what, I think of a scattering length as an actual, mask for particles approaching each other. Is there a picture one can have for this effective range as well?
Yeah, it carries forward in quite a similar way in that if I have a square well potential, the effective range is in the units that we've written it, the size of that square well in some limit. Okay. But just like the S-wave effective range, that only works for certain signs of potential and certain regimes. So it's
I see.
I would say more generally, it's just the energy dependence. But it does have this kind of interpretation as a range of a potential, and you can find that in certain simple potentials.
Okay. Okay, seeing no more questions right now, maybe I'll let you carry on and continue this discussion later.
Okay, great. So the second half of what I want to tell you is about P-wave interactions in quasi-one-dimensional systems. And so here I'm going to take the same atoms with the same Feshbach resonance, but now instead of having a three-dimensional optical lattice, I'll have a two-dimensional optical lattice. And so turning off one of the degrees of freedom, now these particles are free to move in a kind of quasi-dimensional subspace. The way you can think about that is that each of these confinements is a simple harmonic oscillator again, except in one direction, the spacing of the harmonic oscillator is very small compared to the Fermi energy. And we have about 30 atoms per tube, so at zero temperature, the chemical potential would be the Fermi energy of 30 times that weak harmonic oscillator direction. However, that Fermi energy is much less than the confinement gap in the transverse, strongly confined directions, and we crank up this lattice enough so that, just like in the 3D case, there's no tunneling between these lattice sites. So you can think of this as an ensemble of one-dimensional systems. So when scanning the magnetic field for the P-wave resonance, if you're in 3D or a weakly interacting system, you see both of the peaks, both this m equals 0 state that I showed you earlier, and also this m equals plus or minus 1. When I turn on lattices along some of these directions, I can shut down collisions along the x, y, or z direction. And since we have three different, in this experiment, two different directions of optical lattices, there's a couple of different possibilities. If I turn on, let's say, a lattice that along x, then I shut down tunneling there, and then we only have y or z collisions. And there's a little bit of a confinement-induced shifts, but otherwise things look very similar. And then I could turn that off and turn something on the other side. And now when I knock out the collisions along z, then I have this xy peak left because there are two-dimensional collisions, but nothing in z. Now when I turn both on, you might think I just get rid of the x collisions and I have one peak left, but this is what happens. So if I look at what's happening in terms of losses or correlations or anything like that, we saw a really broad response. And actually, we saw this in the lab many years ago and have been just scratching our heads about this. Why is 1D so different? And so this is kind of the mystery that I want to present the solution to. We finally understood this. And the result is kind of strange, that for all the reasons I've just mentioned, identical fermions must interact with exchange odd collisions. And so in 1D, you call that odd wave instead of P wave, because there isn't really an orbital angular momentum in 1D. If you had identical bosons, then particles would be forced to interact with even wave interactions. But what I'm going to tell you is a strange story where actually these identical fermions are able to interact with even waves in this quasi-1 degree of freedom. And that has a lot to do with the story of this strange spectrum I've just shown you. Okay, so the experiment we do is we load these ensembles, and then we examine what states we loaded them into by band mapping the lattice into time of flight and examining the population of the higher bands. And sometimes when you turn on these lattices, you accidentally load higher bands. And you can see that in our kind of images by looking at this slight fuzz over here. At these places, we know that the atoms that are here used to be in higher bands of the lattice. So in the harmonic oscillator picture, that would be population in the one state here. But we have tricks to clean this, which is that because of the anisotropy of confinement in the lattice, sorry, the anharmonicity, we can do some amplitude modulation, clean out the population, and you can see after doing that, we get rid of most of the atoms in this excited state. And then after having prepared our ensemble, we do an analysis by a spectroscopic pulse. So we turn on interactions by, again, spin flipping all the atoms into a background state, into a Feshbach interacting state. That's his B state here. We hold that for a certain amount of time and then do a spectroscopic pulse with a second RF spin flip. To count the success of this second spin flip, we do a Stern-Gerlach separation in time of flight and measure the population in this C state relative to the B state. And when we're going to do this spin flip, we're going to try to spin flip not just to the single particle resonance, but as before, spin flip at frequencies where there should be no single particle flips, but there will be some transfer because these are interacting atoms. The kind of spectra we observe is shown here. There's a big single particle peak, which isn't all that interesting. But then if you look very carefully at this far detuned regime where there should be no transitions for single particles, we do see transitions. So kind of blowing up this scale, we see in fact that the successive transfer scales with the frequency detuning to the 3/2 power. And so this is known, this kind of power law decay is known to be measuring something called a contact parameter, which I don't really have much time to explain today. I think you should just consider a measurement of the contact to be a measurement of the correlation strength between two atoms. It is the probability that those two atoms might be quite close to each other in space with the right wave function for the type of interaction you're looking at. So let's see. I should say that a huge range of people have contributed to the emerging understanding of contact relations. And the thing we're exploiting today is that in these kind of spectroscopy measurements, when I see a power law tail, I measure a correlator, a two-body correlator, which tells me, for instance, about the numbers of pairs at short range. And in equilibrium, this would also tell me if I change the relevant scattering length, then the energy or free energy of the system would change in an amount that's proportional to that contact. So in a sense, it tells me how the interaction strength will tune in a system as a function of the parameter I can tune with Feshbach resonances. So these relations I'm showing you on this slide, I'm not going to go through all of them all, but they were derived for S-wave interacting atoms. And there's another set of relations like this you can find for P-wave interacting atoms. And so again, the contact tells you something like the two-body density matrix. So what things look like at very short range. You know that if I measure in spectroscopy this contact parameter, then I also know something about the form of the two-body density matrix, which is kind of like the G2 function, the short-range correlator for atoms. Okay, so we measure that contact. There's a lot of background to that, but let's say you trust me, I measure a correlator, and now I'm going to show you what these correlation strengths do versus confinement strength or versus magnetic fields. And for P-wave or odd wave interacting atoms in our quasi 1D systems, there's a regime in which things are doing just what we had hoped and expected, that correlations are getting stronger and stronger as I get closer to the place where there's a Feshbach resonance. So the parameters I'm showing you here are not the raw magnetic field parameters for which the data looks like a little bit of a mess, but everything rescaled in terms of one-dimensional parameters. For instance, this length here, L odd, is the odd wave scattering length. It's kind of like the S wave scattering length or P wave scattering length, except in 1D, it scales not only with the scattering volume, but also with the harmonic oscillator confinement length in the strongly confined direction. You see once again that this effective range parameter is showing up, and there's the equivalent of a 1D effective range as well. So we can measure this data. It collapses nicely onto this kind of plot. However, if we get really close to resonance, when the theory had predicted that the interaction strength should get higher and higher, things just turn south. And what's happening within the gray band I'm showing you here is atoms are being lost due to three-body recombination. So this is the atom number after we finish spectroscopy, which we do as quickly as we can in tens of microseconds at the lab. And you see there's already a pretty strong three-body loss. So we kind of notice that once we lose more than about 30% of our data, also the correlation strength no longer tracks what you would expect for an elastic thermalizing system. This three-body loss in quasi-1D, by the way, has been studied by Randy Hewlett's group and Ken Ohara's group in lithium-6. So what we have then is an interaction strength which goes up to, in dimensionless numbers, about 10 to the minus 2. So not unitary, not as strong as the gas can interact. We're limited by these interactions. And then if I go to higher magnetic fields, which is weaker interactions, you see that the data starts to deviate from the curve. And you may be looking at this and saying, your data isn't very good, is it? But in fact, this is a spurious signal of something else happening. What we're seeing there is, even though we had tried to clean out those higher bands, even a tiny population in the higher bands really matters. And we can see that by making the problem worse. As we increase the amount of population in these higher bands, and here you can see a band map picture, this kind of correlation strength where we hadn't expected gets stronger and stronger. And so kind of between these two lines shown on the left panel is all of the things we understand or understood before doing these experiments for odd wave interactions. I should say that, by the way, this theory curve here was written in a paper that came out a few years before we took this experiment, and there are no adjustable parameters. So we really understand kind of this regime of correlations really well. But now beyond this dashed line, things don't really make sense from the perspective of what spin polarized fermions should be doing in the ground band of these 1D systems. And the answer to this strange behavior lies in interband collisions. So what's happening is an atom in the ground band is colliding with one of these few atoms that are in the excited bands. And those excited bands are populated because when we ramp on the lattice, we accidentally and non-adiabatically populated them. And with even a small amount of impurity atoms in that excited band, you end up getting a very strong interaction. So this collision, it has a 1D momentum, which is really well within this 1D regime, where the momentum of the collision is much less than the harmonic oscillator momentum scales. But now in the transverse direction, there's this really high excited energy. And that gap energy, as I've already told you, is much greater than the Fermi energy, any kind of energy we could find in the 1D system. And that's by requirement of being in the one-dimensional regime. We need to have that energy large. And so these interband collisions between fermions allow an interesting kind of wave function. We can have that excitation that is shared between the two colliding atoms in an anti-symmetric way. So there's one quantum of excitation, an atom A and atom B, but now I anti-symmetrize the wave function, just like I always do. And so it's either A or B that has this orbitally excited state. And in a singlet anti-symmetrization, there's a minus sign between them. So the orbital excitation now has all the necessary anti-symmetry to satisfy the requirements of fermions interacting. And what's left over is something in the remaining direction that can be symmetric. So the relative coordinate in that excited direction is this kind of wave function I drew for you at the beginning of the talk, where if I exchange the particles, then the wave function requires a minus sign because of what's happening in the strongly confined direction. But in the weakly confined direction, I can now have S-wave scattering. And that allows me to have three possible continua for this system. One of them is the odd wave interactions I've already shown you correlation plots for. But then there are two other continua. I could either have an excitation in the x or in the z direction, in that confined direction. And if those energies are different, they're energetically distinct continua. So a Feshbach resonance occurs when a bound state hits the zero energy of the continuum. So for the dimer states in 3D, that happens either here or here, now at quite distinct magnetic fields. Also, as I said before, the two different symmetries of ml equals 0 or ml equals plus minus 1 project onto the projection onto the magnetic field axis. Those occur at slightly different magnetic fields. So one of those three dimer channels is shifted, and that presents us with yet another Feshbach resonance. So the basic message I'm trying to explain here is that there are three possible Feshbach resonances, one where the X and one where the Y and one where the Z become resonant with the respective symmetry matched continua. So maybe I'll pause here again and say, ask me questions about this. It's a little bit of a confusing picture because I now need to think about multiple continua.
Well, yes, please do ask any questions, but yeah. And so you're saying that these two extra points, they're the origin of this broad. So it's almost like there's little Feshbach resonances underneath.
Exactly. Okay. The complexity is that now there are new Feshbach resonances that are shifted energetically by an orbital gap.
And so can you do this on purpose, like occupy different orbital levels, I guess, and see additional resonances, I guess, up higher or something like this?
In principle, yes. We haven't occupied anything but the first one, but you're right. Yeah. We should be able to occupy higher resonances and then continue to see further Feshbach resonances.
Yes. And then is there any, I guess, molecular wave function information you can pull out of these things? I guess that might be interesting.
Oh yeah, that's a good idea. I mean, there are new dimers now because in these new channels where I now have even wave interactions that are allowed in these new continua, then the nature of the dimer channel is more like this 1/a² low-lying dimer that we're used to instead of the odd wave dimers. So I know I don't have that much time. What I guess I want to show you is that so far I've just conjectured and shown you a theory plot. So let me show you now experimental evidence that these new continua really hold within them things that look like even wave collisions. So what is the evidence? Well, the smoking gun is that we see a different power law scaling of the interactions near resonance. So if I plot the successive transfer in that spin flip diagnostic, then instead of falling off like omega to the 3/2, it falls off like omega to the 5/2. And that's what you get if you ignore all this p-wave physics and you just write down an s-wave theory for what happens to particles in quasi-1 dimension. So you would see this for bosons that are interacting in quasi-1D, that a contact, which is scaling like 1/momentum to the 4th, in 1 dimension will give you an RF tail that scales like omega to the -5/2. So seeing this nice omega to the 5/2 scaling is really the most convincing signature we saw that we really see emergent S-wave interactions in these new continua. A thing that we didn't expect but came out very nicely from the theory is that there's also a singularity due to the 1D density of states. Once the RF frequency matches twice the gap frequency, you are promoting both of those particles into the third band from the first. And in that case, there's this characteristic 1/energy divergence in the density of states of possible final states. So 1/energy divergences in densities of states are things that are generic to 1D systems. And it's nice to see that appear here. And you don't see that when you do the same kind of experiments and the same kind of spectroscopy for odd wave interactions. Once we know how to find the right power law, we can look at the coefficient of that power law, the coefficient of this, omega to the 5/2 decay, and that gives us the even wave contact. And so now we can measure at a variety of confinement strengths and a variety of magnetic fields what the correlation strength is between the atoms. And we find that unlike the odd wave case, these even wave correlations saturate to something which is comparable to the unitary value. So the interaction per particle is really much stronger from the emergent even wave collisions than it was for the odd wave collisions we had expected to find. Once again, I'm plotting not magnetic field on the horizontal axis here, but scattering lengths. And since there are now two different directions, there's two different even wave scattering lengths, the ones you get from the X confinement or the ones you get from the Z confinement. But still, we can write down an analytic form for this emergent scattering length as a function of the confinement strength and the well-calibrated three-dimensional physics of the p-wave interaction. So that's basically what I wanted to tell you today, that we see these emergent S-wave interactions. And the reason that's exciting is that all of the scaling I was talking about at the beginning that you find for S-wave interacting systems is present here for S-wave interactions that in this emergent form. For instance, as you have a collision energy which gets smaller and smaller, then the range of resonant interaction gets broader and broader. So when I write down, for instance, the scattering amplitude, just like the scattering phases I showed you earlier, the subleading terms become insignificant at low energy because they go away like k to the k cubed. And so you get into this kind of universal regime where we can have a zero range theory for the interactions. And we calculate in the zero range regime because these conditions are met for the Fermi gases in our experiments. So I should wrap up. Let me just say that the conclusions from part one are that when confining pairs in a deep 3D lattice, could see this ladder of on-site interaction energies that allowed us to test the pseudo-potential theory of p-wave interactions for the first time, and also go all the way to unitary elastic interactions. Now, the lattice allowed us to suppress three-body relaxation, but if we can gently add tunneling back again, then maybe we could restore tunneling, maybe xenosuppress losses from three-body interactions, as was done for bosonic molecules, and see some connected p-wave dimers in a lattice. More generally, it seems like there's a lot of interesting physics to explore with orbit, so we could keep this orbital degree of freedom around, reactivate spin degrees of freedom, and have interesting spin orbital phenomena to play with. In the second part of the talk, I told you about emergent S-wave interactions. We measured both odd wave and even wave interactions in these quasi-1D systems, but the even waves really came out being much more promising because we saw strong and near unitary correlations between them, and we expect that we should have an energetically broad set of interactions at low energy. So with that, let me say the mystery of the wide Feshbach resonance was finally solved, and let me thank all the hard work done in the lab by this great team, and emphasize that we did not work in a vacuum. We had fantastic theory collaborators who helped us sort out all the physics of p-waves, sort out what should be happening in 3D optical lattices with p-wave pairs, and understand contact in odd wave systems and even wave systems. So thank you for your attention.
Thank you. I'll give the requisite video clap. And yes, it was really, really interesting talk, and thank you so much for joining us here today. I'll open the floor one more time for questions from the audience. In the meantime, yeah, I was curious about the prospects for the first part of the talk with the ability to sort of access these p-wave interactions, turning tunneling on. Are there interesting many body states you're targeting? How do you go about finding, I guess, maybe topologically interesting states in such a system?
Yeah, so what we've with Anna Maria's team, especially Mikhail and Thomas, whose names I have here, they've looked at the prospects to turn on tunneling a little bit and turn on interactions a little bit to find a kind of Goldilocks regime where losses aren't too strong, but then dynamics are sufficiently fast that we can still observe them, and we can then ask about, is there a xenosuppression regime, or is there a set of parameters where we can see more than just two particles interacting with P waves, obviously.
Mm-hmm.
So the first thing we're thinking we might be able to do is a kind of collective P wave interaction, where actually we tune interactions to be not that strong per pair, but then look at a collective dynamics across many different lattice sites. We've looked at similar things already for S waves. I guess you can think of them in the S wave case, we could initialize the system into a kind of ferromagnetic state that would have an energy penalty to decohere, and so you see a kind of interaction enhanced lifetime to a spin polarized case. So in the P wave case, what we'd be doing instead is polarize the gas in its orbital degree of freedom. So you would have only one of the orbital degrees, the orbital states in every lattice site, and then you would look for the energetic price of dephasing orbitally. And so that's the kind of analogy you construct, where you, instead of looking at spin degrees of freedom, you look at orbital degrees of freedom, and then you use the P wave interaction to tune the energetic gap between that that Dickey state and a decoherent state which has a spin wave in it.
Okay, interesting. And then for the second part, I guess my question was, if you turn on these S-wave like interactions, how much of the fermionic character survives in the kinds of physics that you might want to look for there? Like, are there, can we think of it as like a fermionic superfluid, or does it just become, is it bosonized like for real, or is this, what's the difference there?
In fact, I don't, so far as I can understand, I think there isn't much fermionic character left in the emergent interactions in that quasi 1D. It's kind of like a spin mixture now, where in a spin
orbital
mixture,
degrees of freedom, and
you have so in a spin mixture and with S-wave interactions, yes, the spin degree of freedom is a singlet, but otherwise it's an S-wave interacting gas. Now, there is a Fermi energy. There will be a Fermi energy here too, so there's fermionic character, but not necessarily P-wave character. And so it's not as if they're emergent bosons. They're emergent S-wave interacting fermions. And I think that it's a way of making a different kind of way of making a spin mixture in a spin polarized gas, where, for instance, some systems like metastable helium or chromium have a really fast spin relaxation time. So you can't necessarily make and sustain a spin mixture. With helium, you have pinning ionization. With strong dipole-dipole systems, you have spin orbit relaxation of spin degrees of freedom. And so in this way, you could spin polarize the system, but still have strong interactions without the spin relaxation, because it would be a different, you wouldn't have spin orbit anymore. So it's perhaps a new way of making an S-wave quasi 1D system. It's a bit exotic, but no, it doesn't make, for instance, a topological superfluid if you made the superfluid. Yeah. So far as I understand, that's what this is.
Okay. Okay, well, I think we've hit the top of the next hour. I don't see any other questions right now. So let me just say thank you one more time. And to the audience,
Thanks.
we'll have another VAMOS seminar in 2 weeks with Roya Ozeri from Weizmann Institute. And so we'll look forward to seeing you then. And thanks, Joseph.
Great. Thanks. Thanks for your attention. Thanks for the invitation.
Welcome.